Welcome back. So Edmond will continue with his fourth lecture now. Edmond.
Thank you. In fact, I'm going to continue and start a new lecture. I hope I will be able to finish in the remaining lectures I have today and tomorrow. So as promised, my second lecture is about different problem, that of the jet evolution in a dense QCD medium, what's called generically as jet quenching. And okay, let's go on. So that's the outline. The main topic is about describing jets which propagate in a Quark-Gluon plasma, which is created in heavy ion collision. The jets act as a thermometer, as a probe of the plasma. And to that aim, we have to have a theory for the plasma, we have to have a theory for the jets, and have to have a theory for the interaction between the jets and the plasma. And I'm going to try to develop all that for you now. Let's focus on the dynamics of the jets. So the plasma will be, a simple description will be just a Quark-Gluon plasma at a weak coupling. But I would like to understand how the jets are interacting with this plasma, how the jet evolves, and how the interaction between the jets and the plasma modify the property of the jets. That idea, because these jets are used as observables. Okay, so on the way to the jet in the plasma, I also discussed jets in the vacuum. Some features that probably were not emphasized in the lecture by Michael Spira. And I will not read now the outline, that just serve you as a guideline for what follows. So as a motivation, I will describe a bit some of the observables that we're using at RIC and the LHC to extract information about the Quark-Gluon plasma from the physics of hard probes. So what are hard probes? These are space-time cartoon of heavy ion collision. So this is the time and the longitudinal axis. So these are the two light cones, the left light cone and the right light cones, the left mover and the right mover, two nuclei which collide at time 0 at the point z equals 0. And after they collide, all the partons which are initially present in this nuclei can be released in the final state, and they create a dense soup of partons, which is evolving rapidly, it's highly non-equilibrium. Søren was speaking about that. And eventually, we believe that this soup of quarks and gluons create a Quark-Gluon plasma, not necessarily in equilibrium, but at least with some qualitative properties. And this plasma expands rapidly because of the longitudinal expansion of the medium. The medium expands around the longitudinal axis, and it cools down, and it goes to a hadronization phase transition. So the quarks and gluons hadronize into the hadrons, which are viewed essentially in the detector. So this Quark-Gluon plasma phase lives very shortly, like 10 to minus 23 seconds, which is 10 Fermi. It's a part of the collision, but we don't see it directly. And we like to understand how to probe its properties, how to study the plasma from the final state in the detector, which involves only hadrons. And one of the ideas in that sense is to use hard probes, energetic partons, heavy quarks, jet as thermometers. It looks like a good idea because such hard probes are created very early in the collision, at times about 100 times shorter than the formation time for the plasma, so like 10 to minus 1, 10 to minus 2 Fermi. And after they created, they propagate to the medium or the surrounding medium, they interact with that, and their properties are modified by those interactions. So by knowing how this jet will be created in the vacuum, and by measuring these jets in the heavy ion collisions, one can see the differences, and from these differences, one can infer information about the property of the medium. That's the main idea. Of course, that's a very complicated dynamical system, highly off equilibrium, so it's not clear how to translate the modifications viewed in the data, the observables, into a theory of the property of the matter. But we'll try to do that in perturbative QCD. So I'll start with some observables, which are commonly used. One is called the nuclear modification factor, and it is the ratio of particle production in nucleus-nucleus collisions divided by proton-proton collisions, scaled by what's called the number of binary collisions. So if the nucleus was incoherent superposition of A nucleons, then the production of particles in a lead-lead collision would be the same as the one in proton-proton collision times A to the power 4/3, more or less. And the deviation from the ratio should be AA, sorry, not PA, should be AA, yes. So the deviation of this ratio from unity it's a measure of how different is a nucleus from an incoherence proposition of his nucleons. So it's a measure of the nuclear effect, of the genuine nuclear structure effect. And on this the data plot, you can see comparison between data for neutron gold and gold events at RIC at mid-rapidity, at around 0. This ratio RAA for the gold and RDA for the neutron gold. So this, what we have in the numerator depends upon the system. So RDA for this data here, and RAA for the data there. And you see a very dramatic difference between the data for neutron gold and those for gold. Neutron gold is like proton gold. It's a dilute dense system, while gold is a dense system. So we do not expect a Quark-Gluon Plasma in neutron gold, but we do expect one in gold. So if you look at the data we see in neutron gold, you see an enhancement of the ratio as compared to proton-proton collision. You see more production, at least at intermediate values of PT, in neutron gold than at proton-proton collision. Whereas if you look at gold, you see a suppression, a strong suppression. Now, this enhancement is understood as a consequence of the multiple scattering of the protons from the neutron of the dense gluon distribution inside the nucleus. It's understood, if you want, as a color glass effect, as an initial state effect. And this initial state effect and the consequence in terms of this enhancement here, known as the Cronin peak, was in fact discussed in my previous lecture. It is on the slides, but I didn't have the time to go through. So if you look at my slides will be available on the website of the meeting, you'll find a section which is called nuclear modification factor for proton-nucleus collision. And in that section, I will describe this kind of data, and I will explain. I explain why the gluon saturation in the initial wave function of the nucleus leads to such an enhancement at central rapidities, which is called the Cronin peak. So the Cronin peak is a consequence of what's called initial state effect. It's a gluon saturation effect. On the other hand, the initial state saturation will never predict something like that. So that's clearly an indication of a different kind of physics, and naturally you interpret it as a final state effect, as a consequence of energy loss in the Quark-Gluon plasma. And why energy loss? So let me show you that in a moment. First of all, let me tell you that this data, which is historically important because they were the first data showing jet quenching at RIC, are now overwhelmed and better characterized by the experiment at LHC. These are data from Alice, from the first run at Alice in 2008, I think. Already after the first run, they obtained very precise data, huge statistics. In this case, you see the ratio RAA for two centralities of the lead-lead collision, for central collision and for peripheral collision. So these are the red dots are the most central 5%, whereas here are essentially the most peripheral 70 to 80% data. You see that for both central and peripheral, we have a suppression with respect to unity, but the suppression is stronger for the central event. And if you, that's in line with the expectation that the system created in a central collision is denser than the one created in a peripheral collision. Because here, essentially, all the small x gluons from the nuclei get freed because they have a head-on collision, whereas here the nuclei barely touch each other. So there's only a small amount of matter of gluons which are freed in the final state. But in any case, in both cases, you see final state effect, you see energy loss. So why such a suppression is naturally understood as energy loss? It is explained here. So what I showed you before was the ratio of the particle production, so of the spectra in gold should be here, or nucleus AA, and proton. But now, rather than look at the ratio directly, let me show to you the individual spectra themselves. We did what I showed here. This is the spectrum, this line here is the spectrum of particle production in proton-proton collision. And in the red dots are the spectrum measured in lead-lead collision at LHC at the same energy. So the energy is 2.76 TeV. The continuum line, the PP data, so it's a dn by d2 pt, the number of particles per unit rapidity per unit transit momentum as a function of pt. So the continuum line is a proton-proton data. The red dots, the lead data, and you see a suppression. You see that the red dots are below the continuum line. This suppression is precisely the fact that this ratio here is smaller than 1. It's a suppression. And why there is a suppression? Well, the idea is that the particles, the partons, and then the hadrons have been created in the medium in the same way as in the vacuum, because they're created by hard processes. But after they've been created, they can interact with the medium and lose energy. And you see the spectrum for the creation of the particles as viewed in proton-proton, so it's what's called the vacuum, because in vacuum there is no medium, so it's like, in proton-proton is like a vacuum. The spectrum of particle production in proton-proton collision as a function of Pt, I call it the energy, is rapidly decreasing with the energy. It has a power of, you see, this is logarithmic units. So it's decreasing as a power of the inverse power of the energy with the exponent very large, about 6 to 10. So that's the property of PQCD. Particle production at high Pt is strongly suppressed. Now, assume that any of the particles that produce as in proton-proton now propagates through the medium, and they lose a bit of energy. Then particles which are produced at this energy, now they move to that energy. But if you compare now particles at the same energy, so this energy from here, you see particles which have been produced in proton-proton at that exact energy, and particles that have been produced in lead at a higher energy, because they have to lose some energy to get there. And because their production rate is rapidly decreasing with the energy, there is much less likely to produce particles with a higher energy than with a lower energy. So just by the fact that the particles have lost, you see, this is a particle measured in lead-lead, this is a particle produced in lead-lead or in proton-proton, but the particle produced in lead-lead come out with an energy E, provided they had an original energy E plus epsilon, where epsilon is the energy lost through the interaction, which has some probability distribution Pb epsilon, doesn't matter. So you have to create particles with a higher energy in order to view them in the final state with the same energy as in proton-proton collisions. But since the spectrum for producing a particle in the first place is strongly decreasing with increasing energy, adding a small energy loss here is strongly decreasing the spectrum. So the probability to find a particle with a final energy E in the medium is much more than to find a particle with the same energy in the vacuum, just because of the energy loss. Okay. Now, so far I spoke about observables related to inclusive hadron production. Let me now focus on jets. And jets, as you know from the lectures of Michael Spira, are typically produced in pair-to-pair jets because we have a hard process giving rise to a pair of partons which are back-to-back. They're highly virtual, they're time-like, so they'll typically decay into a bunch of partons which eventually will hadronize, and these are two jets. In the vacuum, the two jets are typically symmetric, so they have the same property, more or less, up to statistical fluctuations. And these two jets are seen in the detector. I'll show you in a moment some pictures of the jet events in the detector. On the other hand, if the hard process occurs inside the Quark-Gluon plasma, say like heavy ion collisions, that's the state of matter just after the heavy ion collision, the valence quarks have passed through, but the gluons have been liberated in the intermediate stages, and they create this plasma. And if a hard process takes place in the plasma, then typically one of the jets propagates to the medium over a longer distance than the other one, because except for very central events, there is no reason that this hard process occurs exactly in the center. So this geometrical bias introduces an asymmetry between the property of the jets because one jet has interacted with the medium more than the other. So it is natural to have, on statistical basis, to have an asymmetry between the property of that jet and that jet, so between the property of the two jets measured in the experiment in lead as compared to proton-proton. And this is called dijet asymmetry, and I'll show the data for it in a moment. And by the way, what is jet quenching? It's a generic name, essentially coined by Dogshitter, essentially, I think, by his knowledge. It's a generic name for the ensemble of the modifications that are suffered by a jet which propagates through the medium, whatever it means. Energy loss in particular, but not only. Everything which makes a jet in the medium different from jet in the vacuum is called jet quenching. And just to make the vocabulary a bit more precise, this is a pair of jets. So this is a hard process of, say, quark scattering leading to a pair of quark and anti-quark which go in the opposite directions, or two quarks go in opposite directions, which evolves through radiation. The jets are experimentally built by grouping together particles which propagate within a cone of a given angle, θ0. It's called the opening angle of the jet. But in the experiment, this opening angle is mostly called air, so don't be surprised by that. In my lecture, it will be denoted alternatively θ0, air, θjet, θ_, just to make life more confusing, so to be sure that you're careful, you're following my lectures. So I intentionally change notations because the experimentally do the same. So we have to be on the safe side with them. But once you define the jet in a conventional way, then you define also what it means inside the jet and outside the jet. What is inside the jet is a jet. What is outside the jet, it means radiation angles larger than θ0. It exists. The θ0, it's an experimental decided, it's a decided value, it's a choice. A jet can have a much wider intrinsic optic angle than the one which is chosen by the experimentalists to define the jet. In that case, there will be a lot of radiation outside the jet core. Or vice versa. The experimentally chosen value of air could be much larger than the intrinsic theta of the jet. In that case, a large part of the inner side of the jet is empty of radiation. But the two notions are not the same. The outside part of the jet may have radiation, like I showed here, but what's called the jet is typically the inner side of the jet. And the modification due to the medium interactions can refer both to the distribution of radiation inside the jet and outside the jet. So I will have both kind of effects in what follows. That's why I want to emphasize that. Good. So now let me return a bit at Rick physics, at the prehistory of heavy ion physics, and to show the first event showing what's called today Di-jet asymmetry. At that time, it was not called Di-jet asymmetry. It was called Di-hadron azimuthal correlations. So it's a distribution of pair of particles with respect to their relative azimuthal angles. So you look at the event, you count all the particles, you then count all the pair of particles, and you correlate them according to their difference in azimuthal angle, so in the plane transverse to the collision axis. And of course, since the event is typically jetty, has some jet structure, there is a large probability that some of the particles propagate in the same direction because they come from the same jet. They come from the same cone. So indeed, if you just plot the two particle correlation as a function of delta phi, of the relative angle between the jets, between the hadrons, you see a peak at delta phi equals 0. So whatever is the direction of the jet, all the particles from the same jet propagate in the same direction. So there is a large probability to find pairs of particles with small angular separation because they're collimated. So in this notation, all the particles which are going in this direction, whatever is the angle here, but the fact that they go in the same direction, they're correlated. There is a larger probability to find particles with delta phi small than with delta phi large, because if delta phi is large, they don't come from the same jet, they're uncorrelated. Of course, you subtract away the uncorrelated part, the background part, you only look at the correlation. But of course, if you have a jet in this direction, then it's very likely to have also a jet in that direction. So if you measure the distribution of the pairs of particles, then it's also natural to find an enhancement when delta phi equals pi, because whatever the jet you look at, if there is a particle in this cone, there is likely to be a particle in that cone because there are two cones back to back. So again, it is natural that the two particle correlations as measured in the event has a peak at delta phi equals pi, which is a bit wider because of good reasons, which you understand. And these two peaks are clearly visible in proton-proton collisions in the red point. Sorry, the histogram, the line. It's also visible in neutron-gold collisions. And the width of the peaks at delta phi equals 0 and delta phi equals pi, both in neutron-gold and proton-proton are essentially the same, which means that there is, in both cases, is the same kind of vacuum physics which fixes the distribution of particles inside the jet. And all that is well understood. So these points here, the distribution here, are very well reproduced by theoretical calculations, say by PTI generators. On the other hand, if one now looks at gold-gold, so nucleus-nucleus collision head-on, the central collisions, then the away peak has disappeared. You see clearly the peak at delta phi equals 0, but there is no peak at delta phi equals pi. So if everything works like if this jet was not existing anymore. And that's what happened. This jet is not visible anymore. This jet has been destroyed by interactions in the medium. And I'll show that the case on more precise data in that sense coming from the LHC. So now, data from the LHC. And I'll start with an event in proton-proton collision, which really shows a clear signal for a pair of jets, the Di-jet event in proton-proton collision. So this is a picture of the detector that's a transverse projection. So the collision axis goes towards you, perpendicular on the cartoon, and this is the longitudinal projection. So this is a collision axis. This is a collision axis, and the transverse projection is like that. Is here. And you can see this intense activity in the detectors in that way and in that direction. These are two jets. They are back-to-back in the transverse plane. They're not back-to-back in the rotational direction because the partons which initiated the jet may have different rotational momentum fractions, so there's no reason for them to be back-to-back in the rotational direction because the original energy or the original rotational momentum was not exactly balanced between the two jets. But the two partons before the scattering were both collinear, so the transverse momentum was zero. So after they scatter, the two jets have to be balanced with transverse momentum, and they are indeed, see one jet, the other jet. And if you, it is customary to plot the particle distribution in a phase space, which is essentially the what's called rapidity, so the polar angle with respect to the collision axis is here. Rapidity eta includes my previous ratio, the same as theta. So this is eta, and this is delta phi, the azimuthal, the azimuth of the particle with respect to the well-chosen axis in the transverse plane, the reference axis in the transverse plane. And you see that there is intense activity centered at 2 points in a phase space, which represent the two jets. So these are traces correspond to the particles in the jet. And these 2 points are separated in azimuthal angle by delta phi gal pi. So if this is phi gal 0, this is phi gal pi. So you see the two jets clearly, even better in this distribution than you see by eyes in the data. Now let's go to lead-lead collisions. And for the time being, I'll look at the peripheral collision. And again, that's a picture of the event in the rotational axis, and slightly the transverse axis as well. And this is the picture of the event in this kinematical plane, rapidity, and an azimuthal angle. You see a bigger background than before. If you compare here, the background was essentially nothing, because why? In this event, we have like 50 particles, 50 hadrons. And among these 50 hadrons, 45 or 40 are in these two jets. So the remaining 10 are there, you can see them, you can count them. Here it's a lead-lead collision, which is peripheral, so you have a few hundreds to 1,000 particles. Most of them are in the background, they don't belong to the jets, but you have a clear signal for two jets, and this is like probably 100 particles each of them. But you still see two jets without any ambiguity. You just see the bigger background. Everything is like a natural extension of proton-proton without much qualitative difference. And now let's go to what's called, let's go to central lead-lead collision. Then one sees events like this one, which are called monojet events. You see a huge background, you see one jet, and you see no other jet. It's like missing energy. Well, it's not missing energy, just that the other jet has melted in the background, because the interaction with the medium was so strong that it has lost energy, and that energy has been transmitted to the particle in the medium. So the whole energy of that would-be jet here now has disappeared and has been transmitted to the background. So one of the jet becomes a part of the background. And also, it's related to the limited resolutions. This experiment, which is ATLAS, can only distinguish jets if they have an energy bigger than 25 GeV. Anything below 25 is seen as a part of the background. So in this case, they see a jet with around 100 GeV, and the other jet has probably something below 25 because it's not visible anymore. So that's a strong evidence of jet quenching, and that's on the same footing as the star data I showed you before with the Di-hadron azimuthal asymmetry. And that's a very clean event, famous event, but now there are many like that from CMS. In this case, the energy of the jet is much higher, so you see clearly both jets. One has 200 GeV, the other one 70 GeV. So there's a huge difference, which is a sign of strong interaction in the surrounding medium. And but you clearly see both events, both jets. So you can indeed understand that that jet has been quenched by interaction with the medium. Now, of course, at the beginning, people were asking, is there any energy missing from the event, or is it possible to recover the whole energy in the background? And it was possible. They made a very careful analysis of the event, and they found that the whole difference of energy between that jet and that jet is indeed carried by hadrons, which are propagating in the same hemisphere as the OA jet. So you see, parton which propagates nearly back with respect to that original jet. So this is delta phi gal 0, this is delta phi gal essentially pi here, and around this jet there are other particles which are at a larger angle, so they're not a part of the jet anymore. And are many, and they're relatively soft, they have energy about 2 GeV, but there are so many, you can imagine how many partons, hadrons with energy below 2 GeV you need to create the difference between that jet and that jet. There are dozens. So this would-be jet here has lost energy by radiating dozens of very soft hadrons which propagate at large angles, and in such a way that they're not a part of the jet anymore, because the jet has an opening which is conventional, and since they're not a part, they're not counted in the jet, but they're in the background. And the total energy in the hemisphere around the leading jet is equal to the total energy in the hemisphere around the away jet. That was very nicely checked by the experimentalists. So it's a matter of energy redistribution, not of missing energy. But still, it was a mystery how can be so much energy redistributed via soft interactions. Because the medium is, let's say this is a 200 GeV jet, and it interacts with a medium where the particles have around half GeV, most of them, 100 MeV to 500 MeV. So it is very, very soft interaction. So how can this soft interaction trigger such an intense energy loss at large angles? That was a mystery, and that was especially a mystery because it was very different from what is the usual fragmentation pattern for jet in the vacuum. And I wanted to tell you that by now we understand that, we believe we understand that, and to give you the theory for that. But before I go to the theory, I also show a few more data, which are more recent data. The modern way to do jet quenching analysis at the LHC, as opposed to RIC. This is what is, I've shown to you before, but the nuclear modification factor for hadrons. Now there's a similar nuclear modification factor for jets. So one is computing, one is measuring the cross-section for producing jets with a given PT, with a given rapidity in AA collision, and one is dividing that by the cross-section producing jets with the same kinematics in proton-proton collision, scaled by the interaction, by the number of binary collisions, by the thickness of a nucleus as compared to a proton, to compensate for the difference in sizes. So again, this ratio should be 1 if there was no nuclear effect, and this ratio is far from being 1. So 1 is here, and here you see the ratio measured by Atlas for 4 different centralities: the most peripheral events and the most central events. And you see in the most central events, this ratio is essentially 1/2. There are less, by twice as less jets with a given PT in lead-lead as compared to proton-proton. And moreover, this suppression keeps does not disappear, so it's still there even for very energetic jets. With jets of 1 TeV with 1000 GeV, they still strongly quench. So a jet with 1 TeV fills a medium where the particles have 100 MeV, and that's very striking. Another observer, which is very important for understanding physics, was called the jet fragmentation function, which shows the energy distribution of the hadron inside the jet. So now, with respect to this cartoon I had before, I'm really looking at the structure at the distribution of partons inside the jet. I don't care what happened outside. The dijet asymmetry was mostly about outside. The away jet has lost energy because the radiation has been pulled to a large angles. But now I'm looking what remains inside the small angle. What remains? What remains inside the jet in the medium is the same as what remains inside the jet in the vacuum or not. What remains inside the jet is called fragmentation function. So the distribution of the hadrons inside the jet as a function of the energy of the jet, of the hadron, sorry, is a fragmentation function. It's a spectrum of the jet. And I compare the spectrum of the jet in lead-lead and proton-proton. This is what the fragmentation function does. So the fragmentation function is a distribution of hadrons in terms as a function of their energy times the energy inside the jet. Experimentalists call the energies PTs, transient momenta. Why they call it transient momenta? Because they refer to the collision axis. And since they look at jets which are at central rapidity, the jets, they look typically propagate in a transverse plane as compared to the collision axis. So for them, all the energies going in the transverse plane are transverse energies. But transient with respect to the collision axis. For me, as a theorist, transient refers to the direction of the jet. So I will use omega for the energy of the hadron inside the jet, and I will use PT, transient momentum, only for a component of the momentum of a hadron with respect to the axis of the jet. So that's why I keep translating, like here. Whenever I show data, I keep translating my notation as a theorist to the data, to the notation from the experimental plots, which have a different meaning. Okay, so this is the distribution of hadrons as a function of the energy of the hadron inside the jet. Measure separately in proton-proton in lead-lead, and then take the ratio. So R is the ratio. It's a nuclear modification function of the distribution of the fragmentation function. So that's the ratio lead-lead divided by proton-proton. the ratio would be 1 if there was no difference. But of course, it's not 1 because there's a huge difference. You can see that it's a strong enhancement in particle production at low energy and at high energy. See, in this case, the energy of the jet is about 140 GeV. 140 GeV is around here, right? 110, 140 is here, sorry. 140 is here. So you see that at energy, which is much more than any of the jet, up to a few GeV, there's a strong enhancement in soft particle production in the lead as compared to proton-proton. Also at energy comparable to that of the jet, so it means for the hadrons, which have the highest energy fraction possible, hadrons which carry like half of the energy of the jet, again, it's an enhancement. Whereas at intermediate energies, so energy of a few dozens of GeV, which are intermediate with respect to that, you have a strong suppression. So there is a pattern. There is a pattern which is very interesting. It's very well confirmed by many experimental results, CMS and ATLAS. And understanding this fine pattern with so small error bars is a challenge for the theory. So this is an example of intra-jet medium-induced modification, as opposed to di-jet asymmetry, which is an example of outside-jet modification. Now, okay, so that was the phenomenological introduction. Now, let me give you the physical picture, the general physical picture, in terms of partons, in terms of weak coupling QCD that we expect, and then to see how to compute that picture. So what is a medium-induced jet evolution? We start with a hard event. So quark scattering by a gluon exchange, giving two quarks in the final state. Both these quarks, this one and that one, are time-like, they fragment. I only follow one of them. So this is one which I follow. This one is highly virtual, so it radiates. Radiates a gluon, we split to quark and quark pair, we split a gluon, then radiates another gluon, splits to two gluon, and so on. So that's the beginning of a jet. That will happen both in the medium and in the vacuum, because there's always virtuality due to the scattering, which allows for radiation, for branching. On top of that, if we are in the medium, if this jet propagates through the medium, also scatter of the medium constituents. So this small red line here, like quarks and gluons from the medium, and this transverse gluons are T-channel exchanges between the particles in the medium and the partons in the jet. The leading parton or the produced partons, they can all scatter. And this collision of the medium constituents have several effects. They can, of course, transfer energy and momentum between the jet constituents and the medium constituents, obviously. They can give additional acceleration, that they can trigger additional radiation, because each of these collisions here acts like the hard event there. It has a less intensity, but it's still an acceleration. So it's a random kick, and this kick can trigger radiation. And because of that, there is additional radiation in the medium, which is called medium-induced, as opposed to the same jet in the vacuum. And is another more subtle property, which has to do with color coherence, with the interference effect, and that I will do that later. Okay, so we like to understand the whole dynamics here, which includes vacuum-like radiation, medium-induced radiation, and collisions. And the first step in that sense is to be sure that we agree, all of us, what's the picture of jet in the vacuum. Of course, that's a baseline. It's not clear how to distinguish it from the general picture, but at least we have to be sure that we understand jet in the vacuum. We already learned about jet in the vacuum from the lecture by Michael. I want to emphasize some aspects which are being important for us fellows, and I'm not sure he has put the accent on them. So, jets are typically generated by a hard event. Here I have taken two examples of hard scattering events, E+, E- annihilation, or gluon-gluon scattering. All these two scattering events have the property that they give rise to a time-like system. So the virtuality of the system produced at intermediate steps, here the virtual photon, and here the final two gluon states, is positive. It's easy to check that from the kinematics. So the virtuality of the final state is the same as the one of the initial state, which is P1 plus P2 for the incoming particle, or P1 for P2 here squared, and P1 and P2 are two on-shell particles, and by just using their own channels, one can easily convince yourself that the virtuality is essentially the same as the energy of the incoming system in the center of mass frame squared times factor of 4. And since this is strictly positive, the system which is created after the collision is time-like. And a time-like system is an unstable system. It can decay. Of course, it can decay, first of all, into a pair of on-shell partons. There is no contradiction. A time-like system can decay into on-shell partons. This is what we'll do in leading order PQCD. So, to leading order, E+ minus annihilation gives a virtual photon, which is time-like, and which decays into on-shell quark and anti-quark. Of course, on-shell quark and anti-quark don't exist, so it would be for sure radiation. But let's stay in PQCD level, they do exist. And similarly, gluon-gluon scattering produces two gluon on shell. But if they are not on shell, if they are time-like too, they will radiate in turn, generating other partons which have even less virtuality, and so on, until the virtuality is decreasing low enough for this particle not to be able to split as partons anymore. And this happens typically when the virtuality becomes of the order of lambda QCD, because in that case, these partons do not exist as partons anymore. They are on the soft scale of the confinement. They have to hadronize somehow. And I will never discuss the mechanism of hadronization, the mode of hadronization, what follows. I will just follow the partonic evolution down to the scale of virtuality of order lambda QCD. So, how to compute the structure of the partonic structure of the jet? So the evolution of the jet from the initial virtuality down to virtuality over the lambda QCD. In that partonic phase, and for sufficiently high energies, one can rely on PQCD, and then the jet fragmentation, the branchings of the subsequent branching of the partons is controlled by Bremsstrahlung. So that differential probability for Bremsstrahlung that we have seen many times so far, I wrote it directly in a form which is divided into soft and collinear limits. So the probability for, say, for this gluon here with energy omega, transit momentum k perp, and emission angle theta to be radiated by the particle with energy E is, in the first approximation, independent of E, and is given by this formula here. The differential probability is an alpha S CR, where R is a representation, the core representation of the leading parton. And then there is the typical Bremsstrahlung spectrum, d omega over omega, which is enhanced, which is logarithmically enhanced for soft radiation, for omega much more than E. And then there is a transverse component of the Bremsstrahlung spectrum, which is logarithmically enhanced for all the K perps. And in this case, for the time-like evolution, what matters is a soft K perp region, which means small K perp as compared to E, which means also small emission angle. So this Bremsstrahlung spectrum amplifies naturally, enhances naturally soft emission, meaning omega much more than E, and collinear emission, meaning theta much more than 1. This is why the jets are strongly collimated. Typically, the jet is collimated because the Bremsstrahlung likes them to be collimated. And this collimation property is further amplified by a property called angular ordering, which is a consequence of interference between successive emissions. And I will spend some time explaining angular ordering. And to that aim, I need first a different concept. Well, let me, before I go to that. So the angular ordering is a consequence of interference. What is interference? We're speaking about a quantum radiation process. So although I show Feynman graphs which are representing amplitude, when you compute the probability, you have to write all the amplitude which count with a given approximation to a given order in alpha s, and then take the modulus squared of them. And of course, that will create interference graphs. Here, for instance, if you want to radiate out one more gluon out of these two gluons here to make a second step in the evolution, the second gluon can be radiated either from that gluon or from that gluon, and the amplitude for the total radiation is the sum of the two amplitudes, and the probability is the modulus squared of this. And of course, when you take the modulus squared, we have crossing terms, which are interference. And these interferences are essential. They are part of the quantum mechanical description. This interference also complicates our life as theorists, because we would like to automatize the jet evolution by writing a Monte Carlo event generator, which iterates branchings again and again, but the interference effects are inconsistent with the classical probabilistic picture. The classical probabilistic picture will be just a sum of modulus squared of single amplitude without interference effect. And it so happened, nevertheless, that the pattern of the interferences is very simple. It leads to a property called angular ordering, and this angular ordering property saves the probabilistic picture and allows Monte Carlo. That's very important. That's why I would like to explain that in detail. So to understand angular ordering, and also for other reasons, it's very important to understand what's called the formation time. A gluon is not emitted instantaneously. In general, a branching process is not instantaneous. In quantum mechanics, there is an uncertainty in the energy of the initial state and the final state, and the difference between these uncertainties defines the typical formation time. And there are many ways to understand formation time from the uncertainty principle. The one I prefer is the one which is relying on the coherence properties between the emitter and the emitted gluon. So here, the emitter is a quark, and this quark emits a gluon at an angle theta. And the gluon is only emitted at the point where it has no quantum overlap with the quark anymore. So the gluon emission can start, but so long as the gluon remains very close to the quark, it's still a part of the quark system. One cannot speak about it as being emitted. So, but eventually, if the system is time-like, the gluon can separate from the quark slowly, And when it separates long enough, large enough, then it's being emitted. What large enough means that the gluon transverse wavelengths should have no overlap anymore with the quark. So long as they do overlap in the sense of quantum mechanics, then they're coherent with each other and they're part of the same system. So the formation time is the time after which the separation between the gluon, which is about to be emitted, and the source quark becomes larger than the transverse wavelength of the gluon. The transverse wavelength of the gluon, lambda perp, is by the uncertainty principle that the de Broglie wavelength is a 1 over k perp, which means 1 over omega theta. And in order to have emission, we like that the transverse separation, delta x perp, between the quark and the gluon, which is the same as the angle of emission theta, times the time delta t from the emission point, become larger than the transverse wavelength lambda perp, which is in turn 2 over omega theta. So you write that theta delta t be larger than 2 over omega theta. And this condition immediately implies that this delta t should be larger than the critical value that I call formation time, which is twice over omega theta squared, or equivalently twice omega divided by k perp squared. So if we look at time smaller than this time, even the gluon has started to be created, we have no idea if this gluon is going to be released in the final state or not. It may get reabsorbed. It will be a visual fluctuation. But for times larger than this value, we know that we can look safely at the process, and if the gluon has been created, it has to be now an independent gluon, an on-shell gluon. Well, thinking about pattern perturbation theory. So this is the time it takes to emit a gluon, and this argument is universal. It comes from an uncertainty principle. It applies to radiation in the vacuum or in the medium. But it will have some twist in the medium that I will return later. In particular, so long as we stay in the vacuum, so this argument is only telling us how long it takes for the gluon to be emitted once the emission process has started. It doesn't tell that the emission has to occur. If this quark here is on shell, or it is space-like, then by energy moment conservation, the emission cannot happen, which means that after a time shorter than this time, the gluon will be reabsorbed back. If, on the other hand, this quark is time-like, then it's more or less clear that this gluon has to be emitted with the probability alpha s coming from the vertex here. And this is what happens if you look now at the process where the quark has been produced by a hard scattering event first, so the quark is time-like, then we can check that the formation time for the emission here, or the gluon, is also controlled by the virtuality of the quark. So the same formation time that I computed before as twice omega divided by k perp squared can be also obtained as twice E divided by Q squared, where E is the energy of the quark and Q squared is virtuality. Just by energy momentum conservation at this time, like vertex here, you can convince yourself that this expression and that expression are exactly the same. So that's a statement that for a time-like system, the formation time is controlled by the virtuality of the emitter. And because the emission is triggered by the hard scattering, the formation time now is typically measured from the hard scattering. So if you want to create a gluon with energy omega and time momentum k perp or angle theta, then this gluon has to be created within the interval delta t of order TF as measured from the hard scattering here. Now, with this information in mind, now let me return to the study of interferences. So to study interferences, you need to have at least two sources, right? Interference refers to emission from two different sources. For instance, I showed you before this cartoon where I had these two sources were the two gluons created by a previous gluon emission, and I was looking at the second emission. Sorry, what I'm doing. Yes, I was showing these cartoons where I had two sources in the first step, and I was getting a gluon out of any of two, and it is giving rise to interference. So I will do the same now. I will study the interference from two sources. And for simplicity of the presentation, I will start with a situation where the two sources are in a color singlet state, say a quark-antiquark pair, as created by the decay of virtual photon of a Z boson. If you look at E+/- annihilation, then quark-antiquark or electron Poisson gives a virtual photon, a time-like, which can separate in quark-antiquark pair, and by the fact that the photon is color singlet, or the Z or W boson color singlet, it's clear that this quark-antiquark pair are in a color singlet state, which is called an antenna. The quark anti-quark antenna in a singlet state is like a color dipole, but this dipole is characterized by the angle, by the emission angle, which was the splitting angle of the visual photon into quark anti-quark pair. So now I have a color singlet antenna, and in the next step I can radiate from either the quark leg or from the anti-quark leg. And of course there is interference effect. More precisely, there is interference effect so long as the emitted gluon overlaps with both sources, because he has to know about both of them, otherwise there is no interference. So clearly, for that to be possible, the emission angle of the gluon, in this case emitted by the quark, has to be large enough. If this gluon was emitted very coined to the quark, he will never know about the anti-quark, and vice versa. If it is very coined with the anti-quark, he will never know about the quark. It is intuitive that gluon can know about both the quark and the anti-quark, provided its emission angle is larger than the emission angle of the antenna. And that's easy to check. Again, you will like that the gluon overlaps with both the quark and the anti-quark. It means you would like that the transverse wavelength of the gluon, which is 1 over omega times its emission angle, be larger than the separation between the quark and the anti-quark at the time of the emission. This separation itself is the angle of the antenna, so theta q bar, times the formation time that we computed before, which is 1 over omega theta q squared. So you see this inequality includes both the angle of the antenna, which measures the separation between the quark and the anti-quark, and the angle of the emission of the gluon, because this is what determines the transverse momentum and hence the wavelength of the gluon. And the condition that the transverse wavelength of the gluon be larger than the transverse separation between the quark and the anti-quark at the time of emission implies, as I was anticipating, that the emission angle with respect to the quark should be larger than the antenna angle to theta q bar. So all emission at large angles, mean out of cone, probe simultaneously the quark and the anti-quark. They can be emitted from any of them irrespectively. So at such large angle emissions, they probe the total color charge of the antenna. And for this particular antenna, the total color charge is 0, because that's a singlet antenna. So such a gluon sees the overall charge, which is 0, and since it sees that over 0 charge, it cannot be emitted. In terms of calculation, if you compute separately the emission from the quark and the one from anti-quark, they're individually non-trivial, but when you add them together to build the total amplitude, you find that the interference term precisely cancels the direct emission term, so the overall probability for the emission at large angle is just 0. So in this case, the effect of the interference is very striking. It's just telling us that the probability to emit a gluon outside the antenna is 0. Which means that this emission in reality that I computed for you before does not exist. What does exist are emission at smaller angles. For instance, this emission from the quark at smaller angle theta q, more than theta q bar, or that emission from theta q, from the q bar at the angle theta q bar more than theta q bar. So instead of having an antenna with interferences, which was quantum mechanical radiation process, one can think of an antenna where there is no interferences, but where all the emissions are restricted to small angles. It's called an angular ordering antenna because the emission angles for the subsequent emission are smaller than for the previous emission. And this argument iterates to the next step. For instance, if I go to one more emission, this emission angle here should be smaller than that one, should be more than that one. So it's very simple. Instead, there are quantum interferences. We should compute amplitude and take the square module squared, but you can forget about that. We just compute classical branching processes as if there were no amplitude, but just probabilities. But we take care to allow only for emissions in which the emission angle are strictly decreasing. Because we know that the would-be large angle emission are in effect forbidden by the interference effect. Once we understand the effect of the interferences, we can effectively take them into account to restrict the phase space for classical probabilistic evolution. And that was applying to the case where the antenna was colored singlet as created by the photon, but of course that's not the most interesting case. Typically the antenna are created by gluons or quarks, so they have color. But the argument applies again. As soon as we have started with a gluon, which creates a two-gluon antenna, so this two-gluon antenna has a color charge, the one of the gluon, obviously. And now let's look at emission at large angles from either this gluon 1 or the gluon 2, large enough to overlap with both gluons. Then these large angle emissions, they see the overall color charge of the antenna, which by color charge conservation is the same as the color charge of the parent gluon. So effectively, the effect of the interference between these two diagrams is to say that the emission at large angle is the same as if it was emitted by the parent gluon. So then, instead of looking at interference graphs, one can consider classical probabilistic graphs. These are now classical probabilistic emissions. They're not amplitude anymore. We have three possible emissions. Emissions by inside the antenna are angles more than the emission angle here, or an emission at a larger angle, but in that case, it automatically occurs from the parent gluon, so it occurs before the formation of the antenna. So having an emission at a larger angle should occur prior to the formation of the antenna. So again, this chain of emissions now is ordered in angle. This angle is larger than this one, which is larger than that one, and also larger than this one. So to summarize, quantum emission with interferences can be approximated as a classical branching process with angular ordering. And this is that's the basis of the Monte Carlo generators for parton showers. Nobody's computing amplitudes. Everybody's computing probabilities, but with angular ordering. And all that applies to jet in the vacuum. We'll see what happens when we have jet in the medium. My last couple of slides on jet in the vacuum, then I'll ask if you have questions, refer to the dominant approximation, to the dominant picture of a jet in the vacuum. We already mentioned before that Bremsstrahlung likes emissions which are soft and which is collinear, and we also argued that angular ordering forces the emissions the color coherence forces the emission to be ordered in angles. So the first angle should be bigger than the second one, and so on. They should not be strongly ordered, but the phase space for the Bremsstrahlung likes small angles. So in reality, the dominant contribution comes from a series of emissions in which the angles are strongly decreasing. This angle is much bigger than that one, much bigger than that one, much bigger than that one. And by the same footing also come from emission in which the energies are strongly decreasing because this gives a logarithmic energy. So a strong ordering in energies give a log of the energy, a strong ordering in angles give a log of the angles, and the dominant contributions are those in which all the subsequent emissions are strongly ordered in both energies and angles. And it's called a double-logarithmic approximation, which have strong double ordering. So the energy of the Riemann particle much bigger than the energy of the first emission, much bigger than the energy of the second emission, and so on. The angle of the first emission might be the angle of the second emission, and so on. You see also that in this physical realization of a jet, the jet opening is fixed by the first emission. The first emission can be anything. It's typically small because Bremsstrahlung likes small emission, but once you set up the first emission, then all the angles should be smaller than that. So the first emission sets the angle of the jet. That's for a theory jet. In experiments, they don't know what the first emission is. They just define, let's look for jet with theta 0 for the 0.4. So that's a definition of the jet in the experimental setup. But when we build a jet by theory, by Monte Carlo, then the first emission of the jet automatically sets the upper limit for all the other emissions. And that's a strict statement for the Monte Carlo, because the Monte Carlo, they're strictly imposing angular ordering. So they build the jet by definition by angular ordering. So if you know the emission of the first angle of the first gluon, you automatically know the maximal opening of the jet, and you can decide that that's the jet opening. Yes?
Can you go back one slide earlier? One slide before this. So this interference, quantum interference giving that result, can you please explain the argument again? I mean, I don't get exactly.
So, physics-wise, my first emission here is a splitting of the gluon into two gluons. That's the physics. That's the actual jet. That's not the Monte Carlo. Monte Carlo is smarter than that. Well, because what happens that after this first emission here, I have physics-wise a second emission at large angles, either from the gluon here or from the gluon there. When I compute this emission in quantum mechanics, I have to take the sum of the amplitude modulo squared. This will give me amplitude, the interferences. The effect of these interferences is precisely the same as if I had an emission prior to the splitting from the parent gluon. That's the effect of the interferences. So a sum of two amplitudes modulo squared with the interferences is a sum of the modulus of a single amplitude. They don't interfere by definition because they're single amplitude. There's nothing to be added here. And that's a classical probability process. Now I define, you see, this diagram, which is a modulus squared of a classical, also a quantum amplitude, I define it as a classical probability. This graph and this graph are very different. This is a cartoon of a classical splitting process. That's an on-shell particle splitting two positives with a probability given by this vertex and by this vertex. Here that was obtained by computing an amplitude in quantum field theory and taking a modulus squared. But what is non-trivial is this inequality from here, because the actual amplitude was not that. On the quantum mechanical side, the actual amplitude was this, because that was the proper time ordering. The physical time ordering was this splitting occurring before that splitting. But the net effect was like if the gluon at large angle was emitted by this. So like if this splitting was occurring before that splitting. Since it is like if, then let's do it like if. So then I just instruct my Monte Carlo to put this gluon emission before that one. It is not what really happens. In reality, this gluon has been emitted in a physical jet after this splitting. Who cares? The final set is the same. If I compute in quantum mechanics, I obtain the same result as here. So that's good enough. The jet is not a space-time picture. It's an energy and angle distribution. So you look at the very end where particles are propagating distribution in angles and energies. You don't care where they're created. So I mean, you may care, but what you measure is not that. And what you compute in this way is not that also. So this calculation of the quantum mechanics just telling me that the final energy and angle distribution is the same as if this particle was emitted before this one. And then you can do it like this. Yes.
Yeah, but I mean, in principle, you have the diagram you have on the right, also on the left, right? I mean, if you look at all the three possibilities where you can emit the red gluon, right?
Right, but that's a different, so when I allow for all the possibility of propagating, of emitting from here, I also allow for the diagram in which quantum mechanical diagram, which I was emitting from there. But now I took it, so when you do time order perturbation theory, you know what happens first. So here I took precisely the case where what happens first is this. If I have the other case where this happens first really, then it is also included here, but with a different probability. So the Monte Carlo contains all the possibilities.
I mean, I'm not interested in the Monte Carlo. I mean, I'm just computing the final state with three gluons coming from one gluon, right? Then I have the large angle gluon emitted first, right?
So if I allow this gluon to emit a gluon at large angles with in the whole phase space, then I cover both the time order graph in which this gluon was emitted before the splitting and the time order graph in which this gluon was emitted after the splitting, but at large angles.
And so when you write the diagram on the right, then the integration over the emission time when you gluon is really just to the vertex before you. I mean, exactly. There's ordering in the time.
I should have added this diagram too if we see in the left-hand side. Yes, it would have been more proper. I should have added also this diagram here. The sum of all of them is the same as. Okay. Good. Yeah. Great. So that's a cartoon of a jet in the double logarithmic approximation. This looks like a lousy approximation, but that's the leading order picture of a jet in PQCD, so it's interesting. And it's also interesting because it can be easily computed analytically, because each gluon, so you want to measure the final gluon here with energy omega and angle theta. This final gluon can be created by direct emission by the leading particle. In that case, it's created with a probability alpha bar divided by omega theta squared. But you can also create this gluon after a sequence of n intermediate gluons emission that we don't measure, and each such a sequence of n intermediate emissions has a factor alpha n, a factor logarithm e divided by e power n divided by n factorial because of the ordering in energies, and a similar factor because of the ordering in angles. We have seen exactly the same kind of strategy for the PDF evolution in DL8. Here is not PDF, it's time-like evolution, it's a jet, but the strategy is exactly the same. You have to order n emissions simultaneously in energies and in angles. You pay the penalty 1 over n factorial for each of the orderings, but you have amplifications to the logarithmic amplification both for the energy ordering and for the angular ordering. And again, this simple series here can be summed exactly. It's a Bessel function, and again, this Bessel function has a simple behavior, asymptotic behavior in the limit where the product of the logs is large, so alpha bar times the log is bigger than 1. In that case, it's just an exponential of the square root of alpha bar times the product of logs. We have many quanta, as many as you can see here. We have exponential growth, essentially, in the number of quanta inside the jet. At the level of this argument, when I was speaking about space-like distribution of Parton distribution, of the Parton distribution, space-like evolution of the Parton distribution, I was arguing that this growth cannot go forever because the partons should start overlapping with each other, interacting with each other, leading to saturation. Here I say the opposite. Here, this growth can go forever. There is no saturation because these particles separate from each other by construction. They go at different angles. So there's never such a thing like overlapping. So there's no, unlike the space-like evolution, which gives rise to a system of partons, which is localized inside the hadron wave function. It stays there. The more and more partons they have to overlap and they have to saturate it. The time-like evolution gives rise to a system which is decaying. These partons, after being produced, they rapidly separate because they go around different directions, so they get just all the ways. And because of that, they don't overlap by construction, so there is never a limitation of this growth. And that's a real a real law in nature to this approximation, unlike the corresponding result for PDFs. So I'm essentially done with the jet in the vacuum, so if there are questions at this level. For the final transforming now, please. Which one? I think.
Yeah. By that diagram, what do you mean? It's not equivalent, right? That 3-gluon vertex square is not equal to the sum of the square of the sum of those two diagrams, right?
No, it's not equal. That's a step in the evolution. So what I wanted to say that okay. Assume I start the evolution with a single gluon, the leading particle. Then the next step in the evolution is this. Then the next step in the evolution can be this plus this. If I ask wave function squared of the whole system, I have to take the modulus squared of that. But if I want to project on the final state with only two particles, with three particles, then this and this does not contribute. So the final state with three particles is just the sum of these two modulus squared. So this is one step of the evolution. And here I have a final state with two particles. Here I have a final state with three particles. Knowing the final state with two particles, I go to that's one step of the evolution. To complete the final state with three particles, I have to take into account these two graphs together. At the final state with two particles, I only had a single graph, this one. I can decide that this is a classical probability. I know the amplitude, I take modulus squared, and I identify that with a classical probability, one for having two particles in final state, and there is no interference term. But when I have the classical probability for having three particles in a final state is obtained in a quantum mechanical calculation by taking the sum of both graphs and taking the modulus squared afterward, and so on. Other question? Okay. Yeah, that's what's called the loop diagram. I'll return to that later because it's not so important. Okay, so far we had only jets in the vacuum. And from now starts the fun, because now we want to add the medium. And as in the previous discussion of jet in vacuum, even for the jet in the medium, I will still focus mostly on the property of the parton shower, how the parton shower is modified by the medium. And to that purpose, I would like to have a medium which is as simple as possible. And so I'll choose the medium to be a weakly coupled Quark-Gluon plasma in thermal equilibrium at temperature T. This is certainly non-realistic. The medium created in heavy ion collision is everything but in equilibrium, and it's not necessarily weakly coupled either. In my defense, I should say that the generalization from a medium which is in equilibrium to a medium which has longitudinal expansion is pretty trivial, just a matter of rewriting equations. And also the fact that the plasma is weakly coupled here refers only to the interaction between the plasma and the jet. And these interactions, I'll show in a moment, are controlled by relatively hard momentum transfers. Not by the energy of the jet, certainly, which is huge, but later by the temperature of the plasma. My momentum transfer will be like 10 times the temperature of the plasma. So I'm towards the perturbative side of the plasma. And for more property of the QGP, as weak coupling, I refer to the lecture by Tony and by Peter. I'll not discuss much. I'll just use the minimum information I need about them.
Oh, excuse me, sir. Sure. So this jet quenching in the medium, I mean, this medium, it need not be in a need not be a thermal medium, right?
Of course, it's not.
When the deconfined phase of like quarks and gluons, yes, you will have this.
It is the confined phase, but it's not. But it's going to be, well, in my lecture, I will use very little things about the property of the medium. But from time to time, I would like to give you estimates from PQCD, and for that estimate, I will use this notion of weakly coupled in thermal equilibrium. Otherwise, you can forget about the statement. What is really important for our time follow is that the jet splitting is controlled by PQCD. Yes, that is important. But the property of the medium itself, I couldn't care less. And the fundamental, but the only aspect I need about the medium properties, which is an aspect which is well justified for weakly coupled plasma, is the fact that the basic physical mechanism for jet, for the interaction between the jet and the medium, is elastic collisions. That's a very non-trivial property. I mean, it's trivial weak coupling, but that would not be the case at strong coupling. But I assume that my jet, in this way, the jet is a quark and a gluon, so the quark splits and quark and the gluon, that's the jet. This jet interacts with the medium constituent, these blobs here, by gluon exchanges. And by assuming that these interactions here elastic collisions which are independent from each other, I implicitly assume that my medium is weakly coupled. Why? Because it's only in a weakly coupled medium that the mean free path between two collisions is much longer than the duration of the collision, then I can distinguish between these different collisions. So that's all I need about the medium. Yes, so it is weakly coupled for sure, but I don't need to tell more precise what is made of and what is characterized by. It is just a medium of weakly coupled color sources which is scatter of my jet via T-channel Coulomb exchanges. And there is a unique quantity which will be important for this scattering, which is the jet quenching parameter. And how do I compute that jet quenching parameter? Depends upon the medium, but that's a different thing.
Edmond,
yes.
You are weakly coupled in the sense of the scatterers being far away,
yes.
Compared to mean free path. How much does it translate on anything that one could call as a thermodynamic property of the medium?
Well, it just means, that would be the case also for a total non-equilibrium system. So that has nothing to do with thermodynamics.
No, for example, no, I don't mean that. I mean, if it is a medium, yes, then it has some thermodynamic properties.
Sorry, what?
If you're saying that it is a medium at equilibrium in temperature T or some such thing, then you are really saying that it has some thermodynamic properties. And what I really want to distinguish is exactly where this particular mechanism would be valid by making a comparison with, for example, the lattice results.
Well, if you're, the statement about the mean free path, you can, if you start with perturbation theory, you know what the mean free path in perturbation theory is 1 over G4. You know the duration of the collision is 1 over G. So if G is small, that's certainly the case. So how to justify that? So I don't care about lattice here because I'm looking at the regime where G is much more than 1. So that would be 10 power 5 Kelvin if you want, whatever.
Now, for example, the usual talk about quasi-particles or even lack of quasi-particles in the medium from TC to whatever 2 TC would affect this picture?
I suppose so, yes. As I said, the medium for me is idealized. So the medium is not my purpose here. My purpose is the Parton-Shaw. How the Parton-Shaw is modified by elastic scatterings. Where the elastic scatterings come from a solid.
But so related to this, Edmond, right? I mean, you don't really need that. This is an elastic scattering or something like that. Would you just need momentum broadening, actually?
Yes, but that I would need the theory for that, and I will build that by really computing. There are other mechanisms for.
Right, but you could probably do pretty much everything you're doing, just saying there is momentum broadening, and this you could define. But
half of my lecture will be devoted to computing momentum broadening. I mean, I don't want to go. I want to be pedagogic. I don't want to just make the minimal list of assumptions which justify my final picture. But you're right. It's more general than that. But I would like to be, pedantic, to go step by step. So, so this is a picture that we just got with Sir and I. So, target momentum broadening. Under the assumption that the momentum broadening comes from independent successive collisions, which give random kicks, and these random kicks add up incoherently in such a way that the particle undergoes, the test particle undergoes a random walking kind of momentum. So we expect that the dispersion P²² in the momentum after crossing the medium over distance L be proportional to SL, and this proportionality coefficient is what is called the jet quenching parameter. It's a property of the medium, a transport property of the medium, and that's the only parameter I will need for what follows, and I will also give a calculation of it under the assumption that we see weakly coupled. So now you may remember that this picture you also see in my lectures on the color glass condensate, my previous lectures. At that time, I was associating this picture with what's called saturation momentum of the nucleus. In fact, the product Q hat L plays exactly the same role as saturation momentum Q², for a large nucleus whose longitudinal width is equal to L. But in the case of the nuclei, the longitudinal width was fixed one forever, was the nuclear width, whereas here this size L is variable because one can cross the medium over distance L, which is depending upon the event. Like in the case of the large nucleus, I will consider the scattering centers here, which are the quarks and gluons in the plasma, are independent from each other, and then their distribution is dictated only by a two-point function, the distribution of the particles, of the color charge of particles. And because it's only a two-point function, I'm exactly the same assumption as the MV model. So the MV model just applies here by definition. You know, there's no difference between independent color charges in a nucleus and independent color charges in a plasma. They're independent color charges, the two-point function. So once again, I will use the dipole picture. So I will compute the transit momentum broadening by using the Acorn approximation. That's the amplitude, that's the complex conjugate amplitude. The transit coordinate of the quark is fixed. Where transit momentum is one I want to measure. So the transit coordinate is x perp in the amplitude, is y perp in the complex conjugate amplitude. The multiple scattering can be summed in the transit coordinate representation in terms of Wilson line. So I have Wilson line for the quark in the amplitude. I have another Wilson line for the anti-quark in the complex conjugate amplitude. And the product of two Wilson lines makes a Q2 bar color dipole. It's just to refresh your memory. So that's my effective dipole now, with the quark at x and anti-quark at y. And my physical transit momentum Brownian distribution, so the distribution of the produced particle in terms of p perp, can be obtained as a Fourier transform of the dipole S matrix. S, X and Y, with the R being the dipole size. And this dipole S matrix is a trace of the product of two Wilson lines, one for the quark and for the anti-quark divided by MC. And as I said, the medium is a distribution of independent color charges. So because they're independent, the only non-trivial correlation is a two-point function, which shows the density of color charge squared per unit volume. So if I look at the density of color charges at I use Lycon coordinates, point x plus x perp and y plus y perp, then this is a delta function because the particle is independent, so I only have a non-trivial result if I measure the same particle twice. So it has to be at the same point, x plus y plus and x perp y perp. And the normalization coefficient is just the color charge density of the partons per unit volume. And since the color charge, it has a factor of g squared, the color charge squared, so I factor out the color charge squared outside to have the g counting explicit. So what remains is a color-weighted density of quarks and gluons. So essentially, it's a number density of quarks times CF plus the number density of gluons times NC divided by the number of gluons, which is NC squared minus 1. And this whole quantity, what I call nu, scales like T cube. It depends upon the color factor, but it scales like T cube for a Quark-Gluon plasma in equilibrium. So if you compare this formula with the one we had in the MV model a couple of lectures ago, you see that the whole calculation from the MV model goes through, provided one is replacing the parameter mu squared there, which was the color charge squared per unit transverse area, by the parameter g squared mu L. G squared mu is the color charge squared per unit volume, and L is the size of the rotational size of the medium. So by multiplying g squared mu by L, you of course get the color charge squared per unit transverse area. Okay, given the color charge distribution, one can compute the gauge field distribution. We have to solve again the Poisson equation because these fields are Coulomb exchanges, right? They're not propagating fields. We have the same Poisson equation we discussed before, and the solution is again given easily in momentum space. This is 1 over k perp squared, so we have, when we take the correlator of two fields, in momentum space, it has naturally 1 over k perp 4. And now, for very small k perp, there is a change in the distribution. This has to do with screening of the color charge. In the case of the MV model, we used confinement to screen the charge. Here, we're luckier in a plasma in thermal equilibrium. There is what's called Debye screening. It is perturbative screening. I'm sure that Tony is going to speak about that. So there is perturbative screening occurring on the scale set by the Debye mass, which is for the Debye mass squared, so for the g squared p squared. That's a leading order result in PQCD. So long as the momentum k perp of the final particle is much bigger than lambda QCD, which is this scale GT, this scale is irrelevant, but we'll see in a moment that we are marginally sensitive to this scale because of the screening properties. So now that we know the correlator of the two-point function, we can compute the dipole S matrix exactly in the way we did in the MV model. We get exactly the same result by identifying what we called before mu squared, the color charge per unit transverse area, with g squared mu times L, and by replacing the screening scale from lambda QCD to the Debye mass. And then the formula I have here is the formula I wrote there with this change of notation. And I wrote it in a slightly different way to emphasize that the medium size L now is a free parameter. So I factor out before I had here the saturation scale squared was implicitly proportional to the size, to the rotational size of the nucleus, but that was a fixed quantity, there was no point to emphasize it. But now my L is a variable, it can change from event to event, it's a random variable, so I better put it in front to make it clear that the exponent here is linear in L. quasi-linear enough. Now, what is this quantity I call jet quenching parameter, the scale-dependent jet quenching parameter? I put a quotation mark, that will be clear why in a moment. So this is obtained from the calculation I just mentioned. It is given by this integration d to k perp which involves the two-point function of the gauge field, because I computed the correlator, what it is here, times the k perp squared factor, which comes because of the compensation between scattering by the quark and scattering by the anti-quark, because of color neutrality. This color neutrality created for me the factor R squared in the exponent and the factor k perp squared inside the integration. And now if you look at this integration here, we see it's d to k perp times k perp divided by k perp force. Essentially, it's a logarithmic integration. And because of this, this is only valid for momenta up to some scale q, which here is specified as 1 over the dipole size squared. So in this logarithm is cut off in the ultraviolet by the dipole size itself. And in the infrared, it's cut off by screening. And I'm sensitive to both scales. So the result of this integration, it's a logarithm with the two scales, the upper limit, which is 1 over R squared in practice, and the Debye mass squared. So what is the physics of this expression here? That's very simple to interpret in kinetic theory. And in fact, this is the alternative calculation of jet quenching parameter as given in textbooks on kinetic theory. The jet quenching parameter can be also defined as the average k perp squared, which is acquired per unit time via elastic collision. So that you need to know the rate for elastic collision, which I give it here, which is G4 times the density of particles times 1 over k squared plus m Debye squared, just rather for scattering for a quark anti-quark, for a pair of two particles multiplied by the density of particles. Okay. So this is rather for cross-section. Integrate over all the k perps with the integrand k perp squared, because I want to compute the average k perp squared acquired by unit time because it's rate. And you can identify this formula and this formula. And also in that standard calculation in kinetic theory, this rate, this integral over the rate with a weighting factor k perp squared is sensitive to the UV scale in a logarithmic manner. And the question is, what sets up the scale for the logarithm? What cuts off the integration? In my explicit calculation coming from the dipole picture, this cutoff comes up naturally. It is the inverse of the dipole size. In a generic kinetic theory calculation, I would need a physical argument to set up the scale. But now I know the scale. The scale is 1 over R squared. It comes out for free. What I said here. Okay, so now that's the S matrix as a function of the dipole size R. Everything is well defined. And now I have to go back to compute the Fourier transform to know the final distribution, the actual momentum broadening in P perp. What I do on the next slide, I compute the Fourier transform by using the equation I had before. Now, so long as I can neglect the weak logarithmic dependence upon 1 over R, which comes to this logarithm, then this integration here is a Gaussian integration and gives me a Gaussian momentum, with the width of the Gaussian being essentially the saturation scale. The same quantity with saturation momentum in the MV model plays the role of the transient momentum broadening in a weakly coupled plasma to leading world. And this saturation momentum squared L here is just the medium size L times the jet quenching parameter evaluated at the saturation scale itself. So the saturation scale appears on the left, it also appears under the logarithm in the right, so it's a slightly implicit equation. The same as the equation I had with saturation momentum in my previous lectures, if you remember. And this also shows that this saturation momentum squared is not just linear in L, although I can think naively. It has an additional slight dependence on L, which is logarithmic to this log up here. So it goes like L times log L, which shows that the physics of momentum broadening is slightly non-local in time. It knows about the whole trajectory. It knows about the whole medium. That's because there are also collisions with very long range, and this collision knows about the overall geometry. And now that I know this scale crystal squared, now I define the jet quenching parameter as the division between average P perp squared, which is Q sat squared of L by L. So I write Q sat squared of L as Q hat L, which defines me Q hat. So Q hat is, if you want, the value of the function Q hat of Q squared that I introduced on my previous slide here, evaluated for Q squared for the scale exactly the same as Q hat L. So I have Q hat here, I have Q hat there, slightly implicit equation, it's not a big deal. But what is important though is that Q hat itself is not, it depends upon the medium size as a whole. So it's a slightly non-local. It's not a local transfer property, it's a slightly non-local property of the medium because of the long range of the Coulomb exchanges. And if you now insert, you should now remember that the number density of particles, quarks and gluons, goes like T cube. You see that in perturbative QC to leading order, Q hat scales like alpha squared times T cube times the logarithm of Q hat again, which is alpha squared times T coming from the cancellation of T cube from here and T squared from there times L. And I think it should be only an alpha s, not alpha s squared, because I have an alpha s squared in Q hat and an alpha s in there by mass. So it's an error here. It should be an alpha s TL under the log. So that's, if you insert the precise value for mu here, this is really the leading log calculation of Q hat in PQCD for a weighted coupled plasma. Before I made the Fourier transform under the assumption that the log dependence of the Q hat is not very important. This is true so long as the typical momentum that I'm looking at is of the order of the momentum given by the multiple scattering of Q hat L itself. Because in that case, I'm controlled by the Gaussian. If, on the other hand, I'm insist in looking at the tail of the distribution of people much bigger than QS, then I'm controlled by a single hard scattering. This can be avoided again from this integration here by expanding the exponent, keeping the logarithm dependence in an essential way, because it is precisely the Fourier transform of the logarithm, which is here, which gives me the right tail at high PT. This is 1 per square. That's rather for scattering. I'm getting back what I put in because I put the rather for scattering here, and I get it back there because it's cell phone. In the single scattering regime is the same. So that's rather for scattering coming as the tail of the high PT distribution for a quark propagated to the medium. This is not the most interesting regime for us here. The most interesting is the one what's called the multiples of scattering, in which you have many successive scatterings, which together give a transient momentum Browning of the order of Q hat L, which Q hat given by this relation. And that, and I'm also finishing precisely in time. This is precisely this distribution, which is this d by d2p computed exactly, so it contains this Gaussian at people over QS, it contains this tail at people much bigger than QS, so these are numerical calculation. So k per times st the same as k per times the distribution, and that's the Gaussian, that's a power law tail in normal units, in regular units. These are precisely the plots I showed to you for the KT Browning in the Henry model. I just take them and put them here. There's no change. Just the reference scale is a different meaning, but the physics of multiple scatterings and of momentum Browning with a Gaussian distribution and a power law tail, rather for tail, is exactly the same in the two cases. So this figure applies to both cases. And I'm done with the transient momentum Browning. And from tomorrow, I'll discuss the medium-induced radiation, which is the most important part. If you have questions. Sure.
In US, there is this collaboration called Jetscape or something, I think. And they have given the values of Q hat as a function of temperature extracted from RIC and LHC data. With respect to their results, how does your formula compare? The T cube is by sort of dimensional.
Well, the analysis that you refer to is very controversial, and that they don't rely on it anymore either. So all the modern phenomenology of the data, which relies on this kind of idea, requires, to describe the data, value of Q hat of order 1 to 2 GeV squared by Fermi. And as a matter of fact, by accident, the leading order result in PQCD is exactly 1 GeV squared per Fermi for temperature of order 1 GeV. So by accident, it's fixed perfectly. But I would say that's an accident. So this gives 1 GeV squared per Fermi, and the 1 GeV squared per Fermi is the preferred value for the data. And that was said by BDMPS a long time ago, but then there was all these other excursions through many other ways to do the phenomenology, was indicating much higher value of Q hat, which explained the connection with IDS, CFT, and all that. And now we return to the situation where the phenomenology likes a small value of Q hat.
So, previous discussions, it was important that the dipole evolution, the nonlinear dipole evolution is taken into account for the saturation to emerge in the first place.
No. That was for the energy dependent saturation. So it was important for having a dense system, right? If you define a nucleus which has no evolution, but with A goes to infinity, it's a dense system. A medium is a dense system. Now, the question is, the question we had in the Quark-Gluon context was, what if the target is a proton? Or it's a nucleus not so large, with a finite nucleus. Then the finite nucleus of proton is a dilute system. And the only way to have a dense gluonic system inside a proton or inside a finite size nucleus is to have high energy evolution, to enhance the gluons by BFK level. In this case, that exists too. But it's less important because the energy of the plasma is not that big. So in that case, a 3-level calculation without energy evolution, it's a good approach, it's a better approximation than in the Quark-Gluon context. On the other hand, here we have the benefit to have a dense medium to start with. That's the Quark-Gluon plasma created after the collision.
Yeah, sorry. What I actually wanted to ask was that you have the exponential growth by BFK, but then you have to somehow come to an equilibrium, and that's the nonlinearity was important there. So isn't some also the effect of this radiation from will also be important in these processes, or?
I bet it is, yes, it is. I don't think I'll have the time to discuss about that, but I did work on that also, yes. There is a generalization of the GMOC for marines to a medium, which is a plasma, which is an extended medium. There is a generalization of BK equation for that. So the whole evolution exists. The effects are less important, but they multiply the density by a factor of 2. They multiply Q hat by a factor of 2, so it's good. They are important numerically. They're not so important conceptually, because the factor of 2 is just a factor of 2, is not an exponential amplification, but still they're important phenomenologically. So you can easily get a factor of 2 if you need a Q hat bigger than the one given by leading order PQC in this formula. If you need it 2 GeV and this gets 1 GeV, no problem. I can give you 2 GeV easily by just taking into account one loop quantum corrections due to radiation. In fact, a factor of 3 comes out naturally. So to answer back to the Rajiv's question, we're more in the situation where it looks like the Q hat in the data is too small. Because if you start with the leading order PQCD and we add then quantum radiation in PQCD as well, we get easily like 3 GeV per square per Fermi, and 3 GeV square per Fermi, it's somehow the upper limit can be accepted by the phenomenology.
I mean, since you referred to that, you actually said that there is a problem with that value of Jetscape, and there are some controversies about it. But they actually had a claim that it had the kind of thermodynamic feature that entropy shows some kind of a rise and then fall from the RIC to LHC. And they wanted to make some big deal out of that. That's why I asked you that, because that would somehow not go with this kind of a thing.
No, I kind of remember that. They always wanted to say that the coupling is weaker at LHC than at, yes, it's something like that. Well, not even Jetscape is not speaking too much about that. Now they have new paper, Jetscape, and where they put together essentially this physics. Now the Jetscape become a framework for combining different mechanisms or different models, and in particular the framework which is favored also in Jetscape, the building block which is favored for the in-medium evolution is what's called the Martini, and Martini is based on BDMPS picture, so essentially they favor this picture as well. And in Martini, the jet quenching parameter is the properties of weakly coupled plasma, so it's not a parameter. What is the parameter? Just the temperature of the medium.
So you motivated Q hat from the kinetic theory picture. Yes. But can it be also motivated from theory of Wilson lines in a non-trivial potential?
I don't like kinetic theory, so my whole calculation here was done on the base of Wilson line. All my papers are done with Wilson line, but at the very end, I cannot not recognize the fact that this result here is also the result of kinetic theory. So this approximation, they are the same. It's not clear. So if we define in this way to all orders, and if we define from Wilson line to all orders, it's not clear that they're the same. It's not the same operator. That's important. This corresponds to Fi plus, Fi plus. This corresponds to product of two Wilson lines. So they're different operators. But in the leading log approximation, they're the same. Yeah, it's a matter of definition. For me, the definition in terms of Wilson lines is a fundamental one, but then there are two light-like Wilson lines, and the question is how do you compute that on the lattice? I mean, we have discussed with Surendra, she's very interested in that. But both definitions involve product of light-like operators. And they're both difficult to evaluate on the lattice. I would say whatever of the two you can evaluate would be good enough. You know, they're not exactly the same, but I suppose they both represent that they're both.
Any more questions? If there are no other questions, let's thank Edmond again.